Okay, so now let's move to our last presentation. The authors will tell you a little bit about the idea of the mate axis. So please, the stage is yours. The screen.
Oh, hi, can you hear us?
Yes, we can hear you.
Zoom just crashed. Sorry, everyone.
Sorry, our Zoom just crashed, but we're rebooting. Anyway, good morning for you. It's evening here. We're presenting from Melbourne, Australia. And except for Maxime Cordeil, who's also helping to present from Byron Bay in New South Wales. This is a fairly large group of co-authors. We worked for a number of years on this work, and so I'd like to start by thanking all of our co-authors, additionally, including the ones who are not on the call today. I
think our screen share is still broken. Yeah, our screen share is very broken. Hang on. Let's see what happens. Do we come back? Okay, we're back. Sorry, everyone. We'll see if we crash Zoom again. I'm just going to switch back to the start. Okay, here we go. And we'll see if Zoom crashes.
It worked perfectly just before.
Okay.
Okay. Yeah, my co-authors presenting today. Well, I'm Tim. I'm the MC, I guess. To my left is Jim Smiley, who'll be presenting a number of use cases of the device that we're going to demonstrate in a minute. To my right is Benjamin Lee, who is going to talk about our user study. And our Zoom has just crashed 3 times in a row. This is glorious. It never does this.
And I'll see what happens if I have the video running. Okay.
And in a moment, Maxime is going to give a brief synopsis of related work. All right. So it looks like we're up and running. So the device we're presenting today, we call the MADE axis, which stands for a modular actuated device for embodied interaction. It's also something that we made, so we're very proud of it. The video that you see now demonstrates 2 people using MADE axes to explore data in a collaborative augmented reality scenario, which was the focus of our user study that Benjamin is going to describe in more detail shortly. And the idea here is that each device maps to a different data dimension, and by placing the devices in different configurations relative to one another, a variety of visualizations can be easily composed. And the actuated slider controls can be used to apply zoom and filter operations. All right, so the reason we're doing this is because we are concerned that data, of which we have a lot, has disappeared into the cloud, into data centers like the one that we see on the screen. And although data visualization is a useful tool that allows us to get a window onto this hidden world, we're still on the outside looking in. And so the point of devices like the ones that we are developing is to bring the data back out into the world in a way that people can interact with in a tangible and much more experiential way. Phenomenologists would argue that our understanding of the world is inextricably tied to physical experience. So that's what we're trying to duplicate. And people have been using physical and tangible embodiments of number and data for a very long time. So at the top of the screen here, we see tally sticks, which have been used, which have been around for many thousands of years. Actually, there's artifacts that are tens of thousands of years old, but in the Middle Ages, they were commonly used to track debts and trade. Abacuses, which we see on the right there, are also ancient, but their sliding bees make them interactive and powerful tools for numeric calculations. And they're still used in many countries to teach the fundamentals of mathematics. And slide rules, like the one at the bottom of the screen, are relatively modern, only a few hundred years old. And they also directly embody numerical functions. Arguably, they were a more human in the loop form of computation, being less prone to error than electronic calculators, because the physical inputs, the sliding parts of the slide rule, give feedback in a way that isn't prone to typos that you might have on something like an electronic calculator. So that's a deep history of devices that embody number and data, and a bit of a motivation for what we're doing. And Maxime is now going to give a survey of more recent work in the field.
Yeah, fast forward in the future with computer systems. The field of HCI has seen actually the emergence of this embodied interaction as a style of interaction that has been basically trying to leverage the use of tangible objects to support like various computing and visual exploration tasks. So rather than doing that just with like wood sticks, actually who can use tangible objects to actual systems, a computing system that can actually perform calculations by using these tangible objects. So this is kind of what's been defined as the embodied interaction. And so those embodied systems very often leverage collaborative setups to allow for multi-user interaction. So the idea behind like embodied interaction is that we do not function in pure thought. We leverage the world around us and our environment to directly perform tasks and achieve our goal, and very often in a very collaborative and social way. So just a couple of early examples of tangible computing, tangible and embodied interaction. There's been a lot of work done a couple of decades ago in the lab of Hiroshi Ishii at MIT. There's been some early exploration of how we can control, for example, geo-visualizations. Not the previous slide still. Geo-visualizations on the left-hand side, or how to perform productivity tasks such as text editing or this type of things with direct interaction with the environment. But still, all this system hooked up to an actual like computer system. Basically, just getting rid of the mouse, the computer, and the screen, and having the system tangible in a social setup. Sorry, next slide, please. Thanks. Just very quickly. Can we get the next slide? I don't see the next slide, but okay, maybe it's there. Okay, so so there's been very little work on using those tangible objects in that spatial sense of creating visualizations. And some work has been done with the tangible queries in the Hiroshi Ishii lab. And and then it was still not the good slide, but okay, this presentation is crazy, but it's okay. No, just forward to the next one. No. Okay, sorry about this, but basically in very recent years, there's been like more and more interest using mixed reality headset to use these tangible objects, because we can track them in our space and we can co-locate them with visualizations, which makes like for a very interesting case to explore data beyond the desktop setup. So we created these embodied axes like a couple of years ago with this 3D rigid frame where we were rendering the visualization using a mixed reality headset, and we were basically supporting visualization tasks in a sort of like a situated manner with the visualization. So we built that concept of spatial coordination, which is like I perform an action on a vertical axis, then the action is also performed on the vertical axis of the visualization. So very quickly, next slide, please. This is kind of a next iteration. It's an iteration of our previous work. We decided to take apart all those embodied axes and create the med axis. And each of these axes are actually those standalone long boxes that the team here is presenting. And they basically present affordances that map to data exploration. So first of all, they have that long shape, which sort of like maps a data dimension. If you like, a typical representation, it embodies that representation. And it also embodies like typical the affordances that you need to perform, for example, range filtering of that dimension, or perform selection with a push button, or change the dimension using the rotary encoder there. Next slide, please. We actually built a few of these, actually, how many do you like 6 or 7 to support multi-dimensional, to support multi-dimensional scenario. The next slide again. Thanks. And we actually, in the paper, we actually present a design space of using these made axes for data scenario explorations and how we map them to the interaction dynamics of visualizations to the made axis affordances. So just in the presentation, Jim will show some exemplar sort of like visualization controls and definition in various visualization setups, basically showing how we can use the made axis.
Okay, so I'm going to show some snippets from some application prototypes we developed. So here's a fairly standard 2D time series chart showing COVID cases in the United States. And so we use the sliders to select the time period that we're interested in. And I've now locked, once the slide changes, I've now locked the sliders together in order to view a fixed time period using the slider actuation. We can impart haptic feedback by actuating the motors back and forth for about 5 milliseconds. So on our y-axis here, we've got a notched switch, basically selecting from 50 states. This next app, when it comes up, is HSV color picker, just mapped to the sliders and encoder, just to show the potential to extend as a modular controller to other applications. And as a VR controller now, so we're tracking our made axes with our Vicon motion tracking system. And we start off our visualization by instantiating or removing a data dimension. The rotary encoder cycles through the data dimensions. We have range selection and manipulation. Sorry, I'm not sure if the GIFs are a bit jittery on your end. And proximity selection. Yeah. So we filter the data with the sliders, and you'll notice that the sliders snap into place in order to match the filter settings in the selected data dimension. So moving into the AR realm, and we really get the full embodiment of the axes here. So we've got a one-to-one physical mapping of 6 data dimensions in this particular case. So this is a collaborative HoloLens application. Each HoloLens is running its own onboard application, and we're streaming the tracking data and the made axes data to both headsets. So with this approach, each made axis becomes a modular building block to quickly create a range of visualizations. A DDoS on demand mode on each axis maps the sliders to select single data points within filtered data. And I'm going to hand over to Ben to talk through how this particular application was used within the user study.
Thanks, Jim. So of course, we conducted an exploratory user study using the setup as Jim just described. The setup that we had involves a tabletop, which is the one that we're actually sitting in front of right now, with 6 of these made axis controllers, as well as 2 HoloLens 2 headsets, which both participants were wearing, each of them once. We also have 6 cylindrical cubes that participants could use to kind of help prop up these axes in specific arrangements, just to better map the aesthetics of a skeleton, for example. We gave them a set of simple data exploration tasks using a fairly simple data set, and we didn't really give them any specific instruction on how to do tasks, so they could do so any way that they wanted. And we analyzed the data looking for general interesting behaviors, as well as feedback from their questionnaire that we gave them at the end of the study. These pictures are all actual pictures from the user study, by the way, and these are all what participants saw in the actual study. So these are examples of 2D visualizations which participants had created. The interesting thing here is that these differed between having the visualizations be standing up vertically or laying down flat horizontally. What was particularly noteworthy is that for visualizations which were vertical, participants did have to crouch down and kneel slightly in order to view the visualizations from a level height. But this did not seem to be an issue, particularly in participant feedback where no one actually had mentioned this. What was especially interesting as well is that there was only ever one instance of participants actually holding up these main axes in order to bring the visualization up to eye level to the eyes. In the case of 3D visualizations, these were of course used less often than 2D visualizations. However, the composability of the main axes made it quite easy for participants to create these visualizations and start actually using them. So for example, we have a 3D scatter plot on the left, a 3D parallel coordinates plot in the middle, which was actually used quite extensively by two groups, and the 3D scatter plot matrix, as you can see on the right. The composability of the made axes also enabled participants to reconfigure and rearrange the visualizations quite easily. So say, for example, the top shows a series of images of participants swapping in and out the axes of a particular visualization in order to change the dimension that's shown on them. Or in the case of the bottom one, we have a parallel coordinates plot where participants were easily able to rearrange the order of the parallel coordinates in order to change the visualization. And lastly, in terms of how groups collaborated and used the overall tabletop, all groups worked tightly together. There was no cases of loosely coupled collaboration. However, in these tightly coupled collaborations, participants would oftentimes point at regions of interest or even take turns controlling the controls on the main axes, such as the sliders. What was interesting was that participants did not necessarily need to make physical space for each other, so they naturally accommodated each other as they went. However, there were, of course, instances of participants making space, there were instances of participants moving around the table in order to get alternate viewing angles on different visualizations.
Okay, so thank you, Benjamin, and thank you, Jim and Max. So just to quickly summarize, we introduced this new actuated device for tangible spatial interactions with data visualizations. And as Maxime discussed, the affordances of the device map well to the interaction dynamics of data visualization. We demonstrated it not only in the augmented reality scenario that Benjamin described, but also in immersive visualizations in virtual reality, and as well as in conjunction with screens. So they work with a variety of different contexts. Our study was qualitative, so you can see the feedback was largely positive, as you can see there. Obviously, there's a lot more we could do to study this device and variations of the device as well, including other types of affordances for interacting with data. In general, our research aims to break down the barriers between people and complex systems and data, as we've seen. So thank you very much for listening. Thank you for bearing with us while we struggled with Zoom to begin with. It worked perfectly in practice, but we are happy to take your questions. Thank you very much.
Thank you very much for your presentation. I love your idea. Do we have any questions from the audience? Yes, we've got the first one, please.
Hi, really cool work, really enjoyed it. It's a really inspiring idea. I mean, I think this whole space of using tangibles to control information visualization, also, for example, formulating queries and all that is an extremely interesting place to work in. So I'm asking a difficult question because I know that there is no easy answer to that, but I'm just would be interested in your ideas about it. So one thing that we always get when we build something tangible for such a purpose is the problem that you can't recreate the tangible setup automatically. So you can't store certain settings. And of course, if you have a difficult analysis task and you work for quite some time on it, you have those parameters and you really would like to somehow persist them in any way, which is of course then hard as soon as you have a tangible controller. I would never argue that for that reason tangibles do not make any sense, but I'm always looking for a good solution or good idea how we could somehow get these two worlds together. Do you have any idea on that?
Yeah, so I guess we started to address that question a little bit by using the actuation of the sliders. So you may have noticed when you changed the mapping to a different data dimension, the sliders sprang into the default position or the previous position of the corresponding filter for that data dimension that was used previously. Obviously, actually positioning the slider in space or repositioning the slider in space is a much harder problem. Yeah, I've seen some interesting work where people put little wheels on devices that represent visualizations. We've got a robot arm over in the other corner of the lab here, which we're interested in using for exactly that problem, but it's tricky, and that's a much more expensive solution once you start introducing robots and things like that. But it's very exciting to try and explore that possibilities.
We also we're also able to add haptic markers within our filter settings as well, which sort of gives a really immediate feedback that, oh yeah, here's a marker that I've added, as you get this little click underneath your fingers as you get to that point of interest.
And the combination of AR and the tangible does mean you can kind of save some state by saving the visualizations themselves. But of course, if you want to recreate that actual tangible interaction, then there's a bit of overhead, rearranging everything. So there's that to consider.
Thank you. Really cool work. Cool discussion. I would love to follow up on this, but maybe later.
Okay, thank you much for your answer. We've got another question from the participant online. Please ask your question.
Yeah, thanks a lot. I'm Raimund Staxfeld. Great work. I really like it. Great work, which is very much close to our research interests as well. One question about different forms. Have you thought about, it's very much in line with Christian's question, have you thought about different form factors? For example, at the moment, you always assume a certain axis, which of course is a part of many visualizations, but there are visualizations which are, for example, circular or have a different shape, or I don't know, did you think about other form factors or about different mappings of your axis? Maybe, of course, you can have a linear mapping also to a circular shape, for example. So maybe you can shortly comment on that.
Am I allowed to mention the chainsaw? The chainsaw idea with the
I still don't like the
with the infinite belt drive.
You use the word chainsaw should be used in conjunction with laser interaction.
You already mentioned it, Jim, so I think you already introduced
what Jim is alluding to is, and we have all sorts of ideas in that regard. Yeah, it's really interesting. I mean, just choosing to interact with axes is just one possible way. But another thing, I think the rotator encoder, the operations you can do with that are really interesting. I'm not sure we mentioned that, but for things like rotating a model in 3D, the rotation encoder is really interesting. And yeah, obviously. There are...
I think if I can add to that as well, very, very quickly, the most of our focus in that space is analyzing like quantitative data, which map nicely to Cartesian spaces, so like lines that you can make parallel or perpendicular to perform comparison, etc., etc. But yeah, like the other reality is like those linear components are just much more easily found in the directly available at the shelf. All those like more complex geometry, I think are super interesting to investigate. But I think the reality is like we're also very limited by all the gadgets that are available. But yeah, I don't know if you found. I don't know if you tried to explore that as well. There's been a lot of work on like passive tangible props. Like there is the work of Yvonne Jensen on the mud stuff. So there's a lot of work on that in the passive space, but not much in the actuated space. Yeah.
Maybe if I'm allowed a short follow-up question, if possible, and that would be, it's interesting because I liked it a lot that you can use that device in different settings. This is a cool thing. So you can, for example, in VR or in AR or even with the display. And my question would be, if you compare, you did not directly do that, but if you compare these settings, for example, in VR, I noticed, of course, you always have these problems of things not being properly aligned. It doesn't really look look like a serious visual analysis environment, VR. So if you just compare that by your experience of comparing like this display-oriented or AR and VR-oriented stuff, what would be the best environment, just maybe with your controller for doing stuff, basically, visual analysis? What do you think? What would be a favorite?
I'll just try to first. I'll answer just my first bit, and then I can hand over to Tim. But so this system is leveraging the iMaxis system that we built a while back, which was all these like embodied virtual axes assembled in space. And so I've demoed that software maybe 5,000 times. And so it's very funny because in VR, you have 90% of people get the interaction. They see an axis, they grab it, they make the visualization. But you do have the good 10% of people who really don't get that VR embodied thing. And my intuition is that with this sort of like more mixed reality setups where you actually see like, you know, the setup on the table with an actual object that you can directly grab and interact, might be a bit more suited for exploration scenarios. Yeah, that's just an intuition. So yeah, maybe there's an interesting study to compare this to VR. Yeah, I don't know if Tim wants to. Or
so I think for us, when we had it going in AR, that was the moment where we really kind of thought, "Ooh, this is exciting" because of the collaborative opportunities, but also just the magic of seeing the data floating around the device. Getting it calibrated took a lot of effort. You can see there's a big QR code on the table, but that's kind of the really exciting part. Also, though, in conjunction with screens is an interesting area, because I think we have settled on a very standard form factor for interacting with screens using keyboards and mice, maybe pointing devices and direct touch. But this whole area of bespoke interfaces for interacting with data, I think is quite interesting. And if you think about how people in say music production use tangible controls to do very complex tasks, it's interesting to think what potential there may be in other fields of productivity and creativity as well for bespoke controls.
Thanks a lot. Really great work. I enjoyed it a lot. Thanks.
Okay, so again, thank you very much for your presentation, and again, a big applause for you.